Welcome to the problem session. So some questions have come through. I think there was a request in the last lecture to go through the last homework that you've had back. So there was that. And then there was also a question about discussing the difference between these different turnstile notations, right? So the thing that either looks like this or the two bars. So for universal validity or for theoremhood provability. So I can say some bit more about that. But if I go through the older homework first, that's further back in the notes. I mean, it's to do with those exercises in chapter 3. So this was exercises 3, 4, 5, and 6. 3, 4, 3, 5, 3, 6 that I'd set.
Was it, sorry, Philip, was it not exercises 4?
But these are not due until tomorrow.
Oh, I see. Yeah.
Was it you that asked me? Sorry, I don't know who you are. But
no, it wasn't me, but I presumed that he meant.
I did actually. When the speaker spoke, I thought, oh yes, it was those exercises 4. But then when I looked, I realized afterwards that they're not handed in yet. They're tomorrow.
Yes. Okay.
I mean, I guess if we want, we could amend that hand-in date and make it just before this talk. I mean, I can give some hints about some of the exercises if people want, but they'd have to ask me what they want. Okay. Oh, well, I've been prepared to go through those exercises in chapter 3, but if that's redundant, let me not do that. Okay, let's look at those, at the exercises in 4.3 anyway. Just a moment whilst I find some bits of paper. So what we see here then is that bunch of exercises. That are there. And I think I'd set for you, which ones did I set? I'd set 4.2a and E, 4.3, 4.4. Okay, well, this will give us also a chance to talk about this single turnstile relation and also the satisfaction relation symbol. So when you talk about a set being consistent, right, so gamma is a set of formulae or sentences, right, is consistent, right? This is about deducibility. What you can deduce from gamma in the rules of proof. And the single turnstile, again, this is all about predicate calculus, the deductive system, rules of proof. So if you've got a good deductive system, I mean, an example in group theory or number theory, we don't want to prove a contradiction like 0 = 1. Right? So we don't want a system to be able to prove some sigma and also prove its negation. Right? So,
Big Boss Welch, yokta.
sorry? Was that a message or a mistake? Maybe somebody's left their mute on off. Okay, so to be consistent means you can't prove this and this for any sigma. Whereas, I mean, if you gamma a set of formulae or sentences, is satisfiable, means we can find some structure, some place in the world where these are true. So some assignment of the free variables, if these are formulae, right, to elements of M that make the formulae true. So our assignments were things in W of M that make all of gamma come out true in M. So for any phi in gamma, W makes phi come out true in gamma here. So, and we also write for this as a shorthand for all gammas, but usually I write this here. So the double turnstile, that's to do about truth in the world, right? Or our mathematical world, right? Single turnstile, it's about provability, just about manipulating symbol strings. So anything you can do like this, these are like operations which are algorithmic. You could run a computer program for. So if you had a computer program that you primed and you told it what gamma was, perhaps through some other Oracle or other computer program, it could deduce, perhaps it could check a proof of sigma from gamma. Now, down here, this has nothing to do with effectivity or algorithms or computerology, right? This is saying there is a structure and phi is true in this structure, perhaps under this assignment if there are free variables. Now, there's no particular reason why one should be able to find a structure in which phi is true. Searching for a structure is not, in general, an effective or algorithmic process. So the completeness theorem is then quite remarkable. Actually, it was in Gödel. He did this in his PhD thesis. Right? So something is universally valid if and only if it's provable. So this is saying something is true in all real-world structures. And this is saying something about, this is like provable from the axioms. A computer could find this phi. Right? And more generally, this says, you know, if for every structure in which all of gamma is true makes phi true, then actually I can prove phi from gamma using my rules of proof. So it's connecting two entirely different things here. And the exercises in section 4 are asking you to think about what these definitions are and try and work with them a bit here. So let's pick something that wasn't there, like 4.2b. Well, actually, what have we got? It's saying if gamma is inconsistent, then for every psi in the language, gamma proves psi and gamma proves not psi here. Well, I mean, a short way to answer this is to look at the previous exercise. Right? I mean, to be inconsistent means there is some sigma for which this does happen. The exercise is saying actually it happens for all psis, not just for one. Right? So exercise 4.1 shows that gamma is consistent if and only if there is some psi so that gamma does not prove psi. So actually being inconsistent actually already means you prove everything, right? So in this case, if you appeal to exercise 4.1, right, this is A is equivalent to C, right? Then to be not consistent, right, would mean you can prove every psi, which of course is just what this is saying here. So 4.2b is really just a rerun of this exercise 4.1, A is equivalent to C. If you wanted to, I mean, that's kind of one way of talking about it. I mean, if you're kind of wanting to kind of approach it afresh, right? Well, you could say something like this. Suppose gamma is inconsistent. Then for some sigma, it proves both. So let's say we've got some proof here from gamma, and we end up with sigma, and there's another proof here also from gamma, and we end up with not sigma here at the bottom. So, I mean, we could put these proofs together, and we have a proof of sigma and not sigma, right, here. So just using a little bit of logic here, we end up with this proof, sigma and not sigma, from gamma. Right? But what we have then is, if you're appealing to tautologies, you've got that P and not P implies anything. This is a tautology. So formally speaking, if I was working within my deductive calculus, right, I could then say sigma and not sigma implies psi. And I would say down here, the justification for this line is this is an instance of a tautology. Here. I've deduced this. Therefore, I can apply modus ponens on the last two lines and get psi. And of course, the psi here, this can be anything. Right? So I could then say, therefore, hence gamma proves psi, where psi is arbitrary. Okay, that's D we've more or less talked about during 4.2D we've talked about, I mean, this morning. That's just saying if gamma is consistent, if every finite subset is.
So for the previous part, don't we have to prove that it's gamma proves psi and gamma proves not psi?
Psi is arbitrary, so I can just replace psi with not psi.
Oh, okay. Yeah.
It's not going to make any difference. Yeah. So for all finite subsets of gamma 0, sorry, all finite subsets of gamma 0 consistent. Okay, so I won't write this all out again because I said this morning. If I can prove a contradiction from gamma, if I can prove a sigma and a not sigma from gamma, this is a finite proof. I only used finitely many axioms. So let gamma 0 be those finitely many axioms from gamma that I used. Then, okay, this is then a finite gamma 0, which is not consistent. Here. And likewise, if I had some in the reverse direction, if there was some finite set that was not consistent, then any superset is not consistent. For the same reasons, if I only need this much to deduce contradiction, and this contains this much, I can deduce a contradiction from these people over here. Let's see, 4, 3, 4, 4. Those were on the homework list. Okay. I was thinking I was going to set 4, 6 for this week, so I won't talk about that. Exercise 4, 5. I don't know whether it's worth doing anything there. Whether you want anything done there. It says try and write down axiomatizations for groups which have in addition various properties right here. That they have less than n elements, or all elements have some finite order down here, or no elements have finite order here. I mean, you may have seen enough of these already. I don't know. Should I do any of these? I mean, Can somebody say yes or no, or do
Yes,
something
can
else?
you do 4.4?
That's one of the things you hand in tomorrow. Um, so, but I mean, just to say something about it then, I mean, the deductive closure is, you know, it's the smallest set that contains T, right? And if you can prove something from it, it's already in there. So you take that idea and then you look at this set here and see whether it's the same. After all, what have we got here? This is a set of sentences which I can prove from T. So what you have to do is just show that T, together with these sentences, conforms to the definition of deductive closure. Right? And actually, it's quite simple. Right? It's
Oh,
actually,
yeah. Sorry, I meant 4.3a about the completeness and theorems.
4.3, this is also something to be handy in, right? It's 4.2a and c, 4.3 and 4.4. Again, I more or less said the answer to this morning in the lecture. Right? If I take a theory of a structure, so this is a collection of everything that's true in the structure. So first of all, that must be complete, must be consistent, right? Because I can't have something true and false in the structure at the same time. So there's no sigma in T such that not sigma is in T as well. So I can't prove from T something in its contradiction. Right? But this says something else. It says show that it's complete. Right? But it's kind of, I mean, once you work out what the theory of A is, it's kind of then obvious because, right? What is a complete theory? It's something such that for every sigma, either sigma is provable from T or not sigma is provable from T. But T is very rich here. Right? For every sigma, T either contains as an element sigma or not sigma, and not both. Right? So it's obvious that from this T, I can prove for any sigma, either sigma or not sigma, because either sigma or not sigma is an element of T. I don't have to do anything in the proof. I just quote one hypothesis, right, down here. So I've just given the kind of verbal argument then there as to why that's complete. B is a little bit trickier, right? I mean, that's more of a puzzle to work out here. I mean, you might think, oh, well, there's two cases, of course. If T is inconsistent, an inconsistent theory is trivially complete because an inconsistent theory, as we've been discussing, proves everything, right? So it's obvious that for any sigma, it T either proves it or not it, right? So this is more interesting when T is consistent, right? So if T is inconsistent, this conclusion is kind of trivially true because T will prove everything. But if T is consistent, then what you could do is assume, okay, T does not prove phi and T does not prove chi, and then ask whether T proves phi or chi. And for the converse direction, going from right to left here, right, okay, you could do a contrapositive. You could suppose T is incomplete. So for some sigma, T does not prove sigma and it does not prove not sigma. So then show that this contradicts what you've got over here. Okay. So somebody said, yes, please, 4.5. And somebody says they're still struggling with 4.1a and trying to work out how the, 4.2a, how the empty set could be consistent. It's kind of logic. The empty set is consistent. Right. I mean, suppose not. Then there is some sigma so that from the empty set we can prove sigma, and from the empty set we can also prove not sigma. Okay, when the empty set is there, we tend to just drop it and just leave a blank space. So this would be saying, just from the rules of predicate calculus, just from the rules of logic, I can deduce sigma and not sigma. Okay, but then you look back through the lemmas and theorems, and you'll find that this is impossible. Right? Because actually everything we prove is universally valid. So we can't prove from nothing at all both sigma and not sigma. Okay.
Did you just say that because it's empty, there is no such sigma?
No, I'm doing a contrapositive. I'm supposing it's inconsistent. If it was inconsistent, then by definition of what inconsistent means, there's some sigma such that I can prove from the hypotheses both sigma and not sigma. But actually the hypotheses is an empty set. There aren't any there. So there are no hypotheses in the empty set. So this means I can prove sigma and not sigma outright using my deductive calculus. But that can't happen because there's a theorem that says, and you should look through and find it, that says anything that's provable without hypotheses is universally valid. Right? It's true everywhere. But I can't have both sigma and not sigma being true in all structures. So check out what the definition of universally valid is. Find that theorem, quote the theorem number, check what universally valid is. Right? Would it technically be right to think of the empty set as the rules of PC? No, I'd rather not, because, I want this to mean, I deduce using the rules of predicate calculus from these hypotheses sigma. So the rules of PC are somehow in this symbol here, not in the empty set. If I write this, or the empty set proves this, right? I'm saying that sigma is deducible in this system. This turnstile symbol stands for the system of PC. So the rules and the system, the axioms, they're all encapsulated in this symbol. Okay. There was a request for me to do some 4.5. So we could move on to that. try and write down aximatizations for all groups which have, in addition, the property and the three properties, they have less than n elements. So A, they have less than n elements. Okay, so what you say is something like, let sigma g be the conjunction of the three group axioms. I can just put an and symbol before them and they end up being one axiom. So I can conjoin them with the and symbol. So that gives me a sentence there. And now I just need something that says they've got less than n elements. So I can just say, here's a sentence, tor n, and it says, it's not the case that there is v1 up to vn, which are all different. So I first say v0 is not different to any of the, is different from all the others. And then I say v1 is different from all of the others. And I do that for however many lines it is. And then at the bottom, I have vn minus 1 is not equal to vn. So this is a sentence, and it's just got all of these inequations here in it. And here there are n plus 1 things because it started at 0. Right? So this says there are not n plus 1 different things. So any structure in which this comes out true can only have less than or equal to n things in its domain. Then if any structure here doesn't have to be a group, if tor n comes out true in M, then the size of the domain of M here is less than or equal to n. Okay. What was B here? No elements have finite order. So the jargon for these amongst group theorists is these are torsion-free groups. You don't have to remember this, but that's their official name. So a torsion in a group is somehow, the predisposition for certain group elements. Once you multiply them together a finite number of times, they get back to the identity element. But in a torsion-free group, that can't happen. No matter how many times you've multiplied the element by itself, it doesn't get back to the identity element. So I think this was done somewhere in the Charles Morgan's part of the notes. So let me just go back to that page. So the relevant point is this line here. So here the formula phi sub n of x, right here, says x times x times x, I mean n times gets you back to the identity element. Okay, which we would naturally like to write as something like this. X to the power n is e. Right? So when we're saying something, a group is torsion-free, it means that for any element x, there's no n, finite n, where you get back to the identity element. So what you could do is take each of these here. This is a set of sentences here. So it's saying, and each sentence says either something's the identity itself, or it's not the case that x to the n is the identity. So here we've got a set of sentences here, gamma. It's not one sentence, it's a set of sentences. And if these are all true in a group, it's going to say for any x, x squared is not the identity, x cubed is not the identity, x to the power n is not the identity. So if you like, any element x, it generates part of the group, a subgroup that looks like z, in fact. Right? But we don't worry about that. Right? So what we've got is that a set here of sentences. So if it's true in a group, it must be a torsion-free group. So I'd say see page 22, right, where that's done. C, it actually says, right, says that this is impossible in the note. All elements have finite order. So this is a torsion group. Okay, so it has no elements like in the line above, right? For every element, there's some power of it that gets back to the identity. So you'll be tempted to say something like this, for all x, these are going to be elements in the group, right? For all x, so well, let me say for all g, little g, elements of the group, there is some n such that g to the power n is the identity. But actually, this wouldn't work because this is not in the language of groups, right? Remember, this is just an abbreviation for g times g n times. Okay, I can write that out using my group function multiplication, and I've got my group identity element, right? But this exists n says there is a natural number, but there are no natural numbers in the groups necessarily, right? So this actually is not in this statement, this is not in the language of groups. Right? So you might then say, okay, right, I could say then for all g, either g is the identity, or g squared is the identity, or g cubed is the identity, or which gets over the idea, right? But again, this is an infinitely long string, right? And our formulae are all finite strings. So this would be cheating, right? We don't have infinitely long. There's no such thing as for us as infinitely long formulae. So here, actually, it turns out, right, we can't axiomatization. And we'll be looking at this.
Is that provable?
Yes, it is. And we will be looking at that. There's no axiomatization for torsion groups. And over here, page 22, this found an infinite set, which I called gamma. This was the set of Charles's phi ends, an infinite gamma, such that I mean, if M is a model of sigma G and there's gamma with a bit of an abusive notation, then this is a group which is torsion-free. But there's no finite gamma that will do the job. This will come from the compactness theorem. Right? We can axiomatize it using an infinite set of axioms. Right? But there's no, it turns out, I'm just saying, we will show this, that there's no finite set that will do the job. Right? So the theory of torsion-free groups is not finitely axiomatizable. So we defined a theory T as finitely axiomatizable if I can find a finite set that'll do the job. If there's a finite T0, it doesn't have to be contained in T, but often it is when we think about it. So that for any sigma, so any sentence sigma, T proves sigma if and only if T0 proves sigma. So it's saying maybe you've got an infinite bunch of axioms here, but there's a finite set which will do just as well. Well, for torsion-free groups, there's no finite set that'll do the job for you. It turns out, right? We haven't got to that point yet. So exercise 4.6. That's going to ask you to show that certain theories are incomplete.
Can you pull the paper down slightly, please?
Yes.
Thank you.
Show that certain theories are incomplete. Okay, so a theory is just a set of sentences. What would it mean to be incomplete? You need some sigma or some phi. Either T does not prove phi, and T does not prove not phi. Okay, so no. what are you going to do about this? Right? Suppose, for example, this was T was the axioms for a group. So there were 3 axioms for groups, right? What you could do is say, right, well, I'm trying to think what to say without giving it all away. If T is the 3 axioms for groups, for example, okay, T is the 3 axioms for groups, then
Is
T
it
does
basically,
not prove the, sorry?
is it basically using commutativity?
That's one way to do that. Yes, indeed. I'm just about to say it. Thanks. Is you could now put down the let phi be the commutativity law. V1 times V0. Well, if this was the case, right, then we would have this. Because what would this mean? Right? Our rules are sound. Anything I can deduce from the axioms, right, is going to be true in any structure in which the axioms are true. By the soundness theorem, if M is a model of T, then M is a model of, let me call this thing gamma. The commutativity statement. Yeah. Then, sorry, I should be saying here, this. By the soundness theorem, if something is a model of T, it's a model of anything I can deduce from T. Our rules of proof are sound. They won't lead us astray. They won't lead us for something that's true in a place to something that's false in that place. So if I can deduce gamma from T, I would know any model of T is a model of gamma. But if we stand back and see what that's saying, that is saying if T is a 3 axioms for groups, this is saying any group here, it's commutative, right? And that's false. Any group M is commutative, which is false. So we can't prove the commutativity law from T. But then the same is true for not gamma. Right? T proves not gamma would imply every model of T is a model of not gamma. So every group M is not commutative, which is false. So T does not prove not gamma. And we've shown then that, okay, the T, the axioms of groups here is not complete. here's a sentence which you can't prove this, or it's negation. So this is the methodology for 4.6 right here. And it asks you, look at the theories in examples 4.7, 4.8, 4.9, right? And show they're incomplete. Well, do the same kind of thing. Look and see what theories are being talked about in those examples, what the models are like, and then think about them and just find something, some feature, which will be true in some of the models, but not in the others, which is exactly what we did here for group theory and the commutativity axiom.